There's a version of the DNA discovery story that goes like this. Watson and Crick were the brilliant theorists, and Rosalind Franklin was the lab technician who took a nice picture that helped them figure it out. That version is, frankly, incomplete. Rosalind Franklin was a crystallographer, not someone who looked through microscopes passively, but someone trained in reading the language of atoms and molecules, how light bounces off crystal structures to reveal shape and arrangement. In 1951, she joined King's College London to study DNA, and she did something most people weren't doing at the time. She asked a really practical question. What if I change the humidity around this DNA molecule? Turns out, DNA can exist in two forms. When it's in wet conditions, it stretches into one shape, what she called the B form. When it's dry, it coils differently. In May of 1952, Franklin took what's now called Photograph 51. It showed, in unmistakable clarity, a pattern that could only mean one thing: a double helix. But here's the thing that historians now point out. Franklin didn't need Watson and Crick to tell her what she was looking at. Her colleagues at the time said she'd talked openly about the A and B forms. She'd written detailed notes analyzing the geometry. And one of her peers, Aaron Klug, studying her research papers years later, said she was 2 steps away from publishing the double helix structure herself. Watson and Crick saw her data she hadn't yet published, and released their model in April 1953. Franklin died of cancer in 1958 at age 37. The Nobel Prize went to Watson, Crick, and Maurice Wilkins in 1962. But the Nobel has a rule. It's never awarded after death, so even if the committee had wanted to include her, they couldn't. The real question isn't whether Franklin deserved the prize. It's this. Why did the story become 3 men solved DNA instead of 4 scientists raced to solve it? Some of it was the times. Women in science were treated as assistants, not peers. But some of it was also choice. Watson's own account, written decades later, downplayed her role. The photographs of the team that made headlines? Franklin was cropped out. She wasn't a victim. Scholars now describe her as an equal contributor who was systematically written out. And that distinction matters. It's not about pity for a great scientist. It's about recognizing that the biggest discoveries in history are rarely one person's breakthrough. They're the result of teams, and some members' names got erased while the story was still being written. Somewhere in the Venetian lagoon, 78 steel gates sit on the seafloor like a giant lock. Each one weighs 250 tons. And on days when the tide threatens, compressed air fills their chambers and lifts them skyward, a mechanical wall between the city and the sea. The whole dance takes about 30 minutes. It's called MOS, the Modulo Sperimentale Elettromeccanico, the Experimental Electromechanical Modules. When it was finished in 2020, after nearly 2 decades of construction and 6 billion euros, engineers called it a triumph. Venice was saved. But something unexpected happened. The gates started closing more and more often. In the first 5 years of operation, MOS closed 108 times. That was manageable. Occasional. The kind of emergency you could prepare for. But in the first 2 months of 2026 alone, January 28th through February 19th, the gates rose 30 times. 30 times in 23 days. At a cost of roughly 260,000 euros per activation, the system burned through about 6 million euros just to get through winter. The barrier that was engineered for exceptional events is now part of the routine. And the engineers who built it are watching with the kind of quiet alarm that comes when something designed to fail gracefully starts failing on schedule. Venice has always been a city defined by water. It's built on wooden pilings driven into lagoon mud, and for over 1,000 years, it stayed afloat through compromise. Rise with the tide, accept the flooding as part of life. But the rhythm of that water is changing. The ocean is rising, roughly 2.5 millimeters every year, because of melting ice sheets and warming seas. Meanwhile, Venice itself is sinking. The city has dropped about 25 centimeters since 1900, partly from the weight of centuries of buildings pressing into soft ground. The math is relentless. Each year the gap closes a little more. Eventually, and this is the part no one wants to say out loud, there may be no gates tall enough. So what comes next? Researchers have mapped out 4 possible futures. One is to strengthen the Osmosis system and even reverse some of the subsidence by pumping seawater underground in a process called hydrogeological recovery. It's technically possible. It's also fragile. It depends on the gates working indefinitely and on people accepting that Venice becomes a city you can only reach by bridge, where ships can't enter and the lagoon's natural rhythms are controlled by a computer program. Other options are darker. Ring dikes, massive concrete walls around the city, would cost up to 4.5 billion euros and would sever Venice from the water entirely. An enclosed lagoon would protect against catastrophic flooding, but would kill the living ecosystem that's been there for centuries. Or there's the option no one wants to name: relocate the city inland, which would cost over 100 billion euros and would mean that Venice, the real Venice, would cease to exist. The heartbreaking truth, according to researchers who have analyzed every option, is that there is no solution that preserves Venice as we know it. Every choice trades away some essential part of the city: safety for economic life, or ecology for prosperity, or culture for survival. The gates will keep rising, the activations will keep increasing, and Venice will keep changing, one barrier closure at a time.
You've probably felt this. You read something interesting, and 2 days later, it's gone. Not because you're forgetful, not because you're lazy. It's because your brain is running a program that's older than electricity. Back in 1879, a German psychologist named Hermann Ebbinghaus got curious about memory. He spent literally years memorizing lists of random syllables, nonsense, DAX, BEF, LOT, and then tested himself to see when he'd forget them. It wasn't glamorous work, but it gave us something invaluable: the forgetting curve, a shape, a pattern, a promise that forgetting isn't random. Here's what happens. Within 20 minutes of learning something new, you've already lost about 40% of it. After an hour, it's 56%. After a day, about 70% is gone. Your brain isn't storing it. It's flagging it as not important. From an evolutionary angle, that makes sense. Your brain protects permanent storage for things that matter to survival. A random fact, a new skill that you're not reinforcing, it gets deprioritized. But here's the plot twist. Ebbinghaus also found that this decay isn't a death sentence. It's reversible. Dramatically. When you review information, really review it, not just skim it. Within a specific window, something shifts. Review it within 24 hours, and your retention jumps from 30% to 80%. Not incrementally, dramatically. And it gets better. When you review again a few days later, the forgetting curve flattens further. Review again a week later, and you've locked it into long-term memory. This is called spaced repetition, and it's not new. But most people don't do it because they're waiting for the willpower moment that never comes. The fix isn't harder work. It's a schedule. Research comparing massed practice, cramming everything into one session, versus distributed practice, spreading reviews out over time, shows the distributed approach wins by 10 to 30%. Not because you're more motivated. Because your brain's memory consolidation works better with sleep and time between reviews. You don't need an app or a system yet. You need 3 review windows: today, tomorrow, and then 1 week later. If you learn something on Monday, review it Tuesday evening. Review it again Wednesday, then Sunday. That's it. By the 3rd review, the forgetting curve has flattened so much that the material stays accessible. You've moved it from short-term to long-term storage. This works for languages, technical skills, names, ideas you read about. The shape of the curve is the same whether you're memorizing Mandarin or learning to code. The takeaway isn't mystical. Your forgetting isn't a character flaw. It's a feature. And the antidote isn't better memory. It's better timing.
Think of your brain like a busy office. All day long, as your cells burn energy, thinking, moving, breathing, they produce a chemical called adenosine. It builds up like dust accumulating on every desk. By late afternoon, that dust is everywhere. Adenosine doesn't make you tired the way pain makes you hurt. It's a signal. It binds to special receptors in your brain and whispers, "Slow down. Rest is coming." The more adenosine accumulates, the louder that whisper gets. After 16 hours awake, the signal is deafening. Here's what nobody tells you. Caffeine doesn't remove adenosine. It doesn't clear the desk. It doesn't generate new energy. Caffeine is a shapeshifter. It's similar enough to adenosine that it can fit into the same receptors. But when caffeine sits in that spot, it doesn't send the rest signal. It just blocks adenosine from doing its job. You're still making adenosine. It's still building up. But your brain can't hear it. So you feel alert. Not because you have more energy, because the fatigue signal is muted. Caffeine hangs around in your system for about 5 to 7 hours. It slowly metabolizes, breaks down. As it fades, adenosine finally gets access to those receptors again. All the adenosine that's been piling up all that time hits your brain at once. That's why 3 p.m. coffee makes 6 p.m. worse. You didn't earn the crash. You delayed the signal. The fatigue was always there. You just temporarily blocked yourself from feeling it. The thing that made you alert at 2 p.m. is the same thing that makes you crash harder at dinner time. It's not a second wind. It's a blocked wind that finally breaks through. This doesn't mean coffee is bad. It means adenosine is smarter than we usually give it credit for. Your brain isn't lazy when it signals rest. It's doing exactly what it should, keeping track of your energy budget and asking you to balance it. Understanding that caffeine masks a signal instead of solving the problem changes how you listen to fatigue. Instead of fighting it with more caffeine, you start to trust it.
TikTok's algorithm is treated like a mysterious oracle. Shadow government, mood manipulation, the works. But the actual mechanism is almost embarrassingly straightforward. It's not trying to read your mind. It's trying to predict one thing: what you'll tap next. That's it. No personality profiling. No political brainwashing. Just, will you watch until the end or will you swipe? And if you watch until the end, will you come back? When you upload a video, TikTok doesn't send it to millions of people and hope. It sends it to your followers, a small test audience, and watches what happens. If your followers finish the video quickly, if they like it, save it, share it, or comment, TikTok takes that as a signal. This creator knows how to hold attention. Time to show it to people who don't follow you yet. The completion rate threshold sits at about 70%. 7 out of 10 viewers need to watch to the end. That number was 50% in 2024. TikTok raised it in 2026 because the algorithm got better at predicting fewer videos needed before the system was confident. It's getting pickier. Instagram and Facebook were built around the social graph, the people you know. TikTok was built around the interest graph, the content itself. That's why an unknown creator with 3 followers can go viral on TikTok, but on Instagram, follower count is destiny. TikTok doesn't care who made the video. It cares if it's good. This is why creators on TikTok say the algorithm feels fair. and why people on Instagram complain that it's broken. TikTok's fairness is built in. The system doesn't reward popularity. It discovers talent. That's the actual business model. Find great content, deliver it to people who want to watch, keep them scrolling, keep the ads running. Here's where it gets interesting. In January 2026, TikTok signed an agreement to divest 45% of its U.S. operations to a consortium led by Oracle, Silver Lake, and MGX. What that means in real terms, the U.S. version of TikTok is being retrained. Oracle is taking user data that only comes from the United States and rebuilding the recommendation system from scratch. Separately from the global version, with American engineers. The geopolitical drama grabbed the headlines, but the technical detail is the real story. TikTok's U.S. recommendation algorithm, the one running on your phone right now, is about to work completely differently than it did 3 months ago. Faster, maybe slower, maybe different priorities. Nobody outside Oracle knows yet. The algorithm is transparent when you actually look. But we don't look. We just feel like we're being watched and move on.
Most people think of bacteria as lone wolves, isolated cells just trying to survive. But that's not what's happening at all. Bacteria are actually having conversations. And these conversations are so sophisticated that we're still learning to read them. About 30 million years before humans evolved language, bacteria had already invented a system for collective decision-making. It's called quorum sensing, and here's how it works. Each bacterium produces chemical molecules called autoinducers, essentially chemical sentences. These molecules drift out into the environment. As the bacterial population grows, these signals pile up, and bacteria monitor this chemical buildup like voters checking the ballot count. When the signal reaches a threshold, when enough voices have spoken, the bacteria suddenly shift behavior. They might turn on virulence factors, start producing antibiotics, or light up with bioluminescence, all at once as one organism. The crazy part? They only do this when the population is dense enough to make it worthwhile. A single bacterium producing toxins is pointless. It won't survive the immune response. But 1,000 bacteria, all producing toxins together, that's a strategic threat. So bacteria have solved a game theory problem that took humans centuries to articulate. Coordinate your expensive defenses only when the collective benefit outweighs the individual cost. This system was discovered by accident in the 1960s. Scientists were studying a glowing bacterium found in Hawaiian squid, Vibrio fishery, and noticed something strange. The light production only switched on when the bacteria reached a certain density. No density, no light. For 20 years, nobody believed this. It seemed too intelligent, too intentional. But in the 1980s, researchers identified the actual molecule, a chemical called acyl homoserine lactone, and the genes that produce it. And suddenly, everywhere they looked, they found it. In plant pathogens, in dental biofilms, in our own gut bacteria. What makes this remarkable is the simplicity. There is no brain in a bacterium. There's no executive decision maker. Just a chemical receiver, a threshold, and a genetic switch. And yet, through these simple rules, millions of single-celled organisms coordinate behavior as if they were thinking together. Today, your own microbiome is running this algorithm. Your gut bacteria are sampling their environment, sensing the density of neighbors, and making collective choices about which genes to express. They're deciding, chemically, whether to be friendly or aggressive, whether to produce compounds that help your digestion or signal for immune attention. And they're doing this without any central authority, just through the accumulated voice of the population. It turns out that intelligence isn't about having a brain. It's about being able to sense your environment, coordinate with others, and adapt based on scale. Bacteria have been doing this longer than trees have existed. We're just now learning their language.
Here's a historical puzzle. The printing press was invented in Europe in the 1450s. It spread rapidly. By the late 1400s, Jewish printers had set up presses in Constantinople itself, producing books in Hebrew. And yet, for nearly 250 years, the Ottoman Empire, one of the world's largest and most sophisticated empires, refused to print books in Arabic or Ottoman Turkish. It wasn't that they didn't know about printing. It wasn't that they couldn't afford it. It was a choice. A deliberate, repeated, legally enforced choice made by sultan after sultan. In 1485, Sultan Bayezid II issued a decree banning the printing of books. 14 years later, in 1515, Sultan Selim I reinforced it with another ban. The stated reason was explicit. They feared that biased persons might tamper with the sacred religious texts. The Quran, in particular, was considered too holy, too important to be entrusted to the mechanical reproducibility of a printing press. What if someone introduced an error? What if a printer, intentionally or not, altered a single word of God's revelation? It's an interesting fear, because it assumes that sacredness lives in the exact arrangement of letters, not in the meaning they carry. And it assumes that handwritten manuscripts, copied by human hands, subject to human error and human ambition, were more reliable guardians of truth than machines. But there's a deeper institutional reason, one historians have pieced together over time. The Ottoman Empire's bureaucracy and education system depended on scribes, thousands of them, trained in the calligraphy and careful copying that made a manuscript valuable. These scribes had real power and real employment. Printing would have disrupted that entire system. It would have made knowledge reproducible at scale in a way the scribes' monopoly couldn't control. Here's what makes this even more striking. The restrictions only applied to Arabic and Ottoman Turkish. Hebrew books? Those could be printed? Christian books? No problem. So the concern wasn't really about printing spiritual danger. It was specifically about damens their texts, damens their knowledge, damens their 20 to control. It took a Hungarian convert to Islam named Ibrahim Mutefrika, working under the patronage of the Grand Vizier, to finally overcome the opposition. Around 1720, more than a century after Johannes Gutenberg, the first official Arabic printing press was allowed in Constantinople. Their first printed book came out in 1728. By then, European publishers had been printing scholarly texts, literature, technical manuals, and religious works for 270 years. The Ottoman Empire had preserved a certain cultural stability through that prohibition, but it had also, slowly and invisibly, fallen behind. Innovation happens at the margins, with distributed reproducibility, with the ability to print, circulate, and build on ideas at scale. Once you say no to that, you're choosing stability over dynamism. And history has a way of punishing that choice.
If you've ever walked through Tokyo Station, you've stood under a ceiling that shouldn't exist. Not anymore. The ornate domes, the coved plasterwork, the carved eagles that look down from above the main concourse. All of it was gone by the spring of 1945. Destroyed in firebombing. Vaporized, along with most of the wooden structure above the main floor. And yet, when you look up today, you're seeing something that was perfectly reconstructed, a precise echo of something lost. Tokyo Station remembers what happened to it, and what it chose to become. Tokyo Station opened in 1914, designed in European Baroque style by a Japanese team studying Western architecture. It was deliberately grand, deliberately modern. In the 1920s, when Japan experienced a devastating earthquake, the Great Kanto Earthquake of 1923, Tokyo Station survived the tremors and the fires that consumed much of the city around it. The dome held. The structure endured. It became a symbol that Japan was building something that lasted, something permanent, something that refused to fall. Then came 1945. The firebombing campaign against Tokyo killed over 100,000 people in a single night on March 10th. The city was incandescent, and Tokyo Station's north and south domes, those elegant, soaring structures that had survived the earthquake, were consumed. The third floor was largely destroyed. The interior, which had been beautiful and functional, became a gutted shell. What had been a statement of permanence became a ruin. Here's what happened next, and this is the part that says something about how a damaged culture decides what to recover. The architects and engineers didn't design something new. They didn't try to move forward into a different aesthetic. Instead, they went back to the original blueprints from 1914 and 1923. They studied the photographs of the ceiling before the war, and they rebuilt the octagonal and coved ceiling, with its original eagle carvings as precisely as the evidence allowed. It took decades, but eventually, what you see is what was there, or rather what should have been there, restored as faithfully as memory and craft could manage. In 2003, Tokyo Station was designated an important cultural property, not despite its history, but because of it. Because it's a building that was simultaneously destroyed and preserved. It contains both the war and the recovery. Every traveler who passes through that concourse walks under a ceiling that exists, because someone chose to remember, not to replace. It's a very particular kind of permanence, the kind that only comes after loss. Most people don't think about this when they're catching a train, but the building does. It's been thinking about it for 80 years.
In the 1990s, a Swedish psychologist named Anders Ericsson studied elite violinists. The best ones had practiced about 10,000 hours by their early 20s. The finding got boiled down to a headline, 10,000 hours to mastery. And it's stuck. It's everywhere. It's become the ultimate motivational myth. Put in the hours, and you'll be world-class. Here's the problem. That's not what Ericsson said. And more importantly, it's not what the research shows. Ericsson's claim was narrower and much more interesting. The elite violinists didn't just practice 10,000 hours. They practiced in a very specific way. They focused on improving weak points. They had a teacher, someone experienced, guiding them. They concentrated deeply. That specific type of practice, which Ericsson called deliberate practice, was what separated masters from competent amateurs. But even 10,000 hours of deliberate practice isn't universal. A professional musician with 15 years of daily practice might never reach concert hall excellence. A chess grandmaster and a golf pro might reach peak performance in very different timelines. Why? Because the relationship between hours and skill isn't as clean as a motivational poster suggests. A meta-analysis looked at research across different fields, games like chess, sports like swimming and tennis, music performance. What percentage of skill variation could deliberate practice hours explain? In chess, 26%. In music, 21%. In sports, 18%. Translation: someone can have the exact same number of practice hours as an expert and still plateau far below them. Practice hours are one variable, not the variable. What else is happening? Natural ability, the quality of coaching, the structure of the practice. Whether you're training for something that's already saturated with talent versus something newer. How early you started. Genetics matters. Environment matters. The type of feedback you're getting matters. Erickson's core insight wasn't practice a lot. It was practice deliberately, with focus, with feedback, under expert guidance, targeting your weaknesses. Once you can play an instrument okay, or code at a functional level, or speak a language passably, you hit something Erickson called the OK plateau. You've done it enough that it's automatic, and automaticity kills improvement. You can log another 5,000 hours of the same thing, and plateau stays flat. This is what most practice actually is. Repetition without intentional improvement. You're playing the same song the same way. You're writing the same style of code. You're having the same conversations in the same language. The clock keeps running, but you're not improving. Deep practice is uncomfortable. It targets the gap between where you are and where you want to be. It requires feedback. It requires someone or something saying, "That's not right." Try it this way. Most people avoid it because it's not fun. But it's the only thing that actually moves the needle. If you want to get genuinely good at something, the 10,000-hour frame is both too much and too little. Too much. Because mindless repetition won't get you there, no matter the hours. Too little. Because focusing on the clock misses the real question. Are you practicing deliberately? Do you have feedback? Are you targeting your weaknesses? A musician with a great teacher practicing 2 hours a day with intense focus will improve faster than someone logging 10 hours a day alone, repeating old habits. The quality of the practice structure determines the pace of improvement far more than the hours. So the honest version of the rule is this: mastery requires sustained, structured, deliberately difficult practice over years. How many years depends on the field, your starting point, the caliber of your feedback, and yes, some factors you can't control. But the hours aren't the variable that matters. The intentionality is.
You wake up, your alarm goes off, or sunlight hits your eyes, or you just surface from sleep naturally. You expect your brain to turn on, instantly, like a light bulb. Instead, you're foggy, disoriented. Your thoughts feel like they're moving through water. You reach for your phone, and it takes 2 tries to unlock it. Your motor control is off. This usually lasts 15 to 30 minutes, sometimes longer. Most people blame themselves. I'm not a morning person. I need more coffee. But what's actually happening is neurological, not personal. Waking up is not a switch. It's a transition. Dozens of brain regions have to coordinate. Different neurotransmitter systems have to trade places. The systems that kept you asleep have to power down. The systems that drive alertness have to power up. This is called sleep inertia, that temporary grogginess and impaired thinking that comes with waking. It's caused partly by residual delta waves, the slow, deep brain activity characteristic of deep, restorative sleep. Those slow waves don't vanish the instant you open your eyes. They linger, especially in parts of your brain like the cortex. So you're half awake, half asleep, neurologically speaking. Sleep inertia gets worse if you wake suddenly from deep sleep, from stages 3 or REM. You're yanked out of the deepest, slowest part of your cycle. That's a bigger neurological distance to cross. It's why waking from a dream to your alarm feels more jarring than gradually waking as your sleep naturally lightens. It's also why you feel worse if you sleep too long. If you sleep 10 hours instead of 8, you're likely waking from a deeper stage, and the inertia is heavier. Your brain is still doing its job, just protecting you. Deep sleep is when repair and consolidation happen. Waking from that abruptly is a jolt. The inertia is the transition tax. Sleep inertia typically lifts after about 30 minutes to an hour. Sunlight, movement, and the passage of time all help accelerate the transition. Light entering your eyes tells your brain it's daytime. Movement activates your motor systems and pushes alertness higher. Adenosine drops as your circadian rhythm climbs. You don't actually need to do anything special. Your brain will finish waking on its own. You're not broken. You're just in the middle of a process that takes time.
In the mid-1980s, when Costco opened its food courts, they set a price, $1.50 for a hot dog and a soda. The combo has not moved since. Adjusted for inflation, it should cost around $4.50 today. Costco loses money every time you buy one. They've been losing money on it for 40 years. And they're never going to stop. This is the most expensive brand promise in corporate history. Costco's whole business model is built on membership. You pay to shop there. The margins on products are razor thin because Costco makes its real profit from the membership fee itself. Everything in the warehouse, the low prices, the return policy, the services, exists to prove that membership is worth it. The hot dog is the symbol. It's the thing everyone notices. It's the thing that stays the same when everything else goes up. Costco isn't trying to make money on food. Costco is using food to tell you a story. We keep our promises, even when it costs us. The founder's name was Jim Sinegal. And there's a famous moment in Costco history when someone told him that the hot dog price needed to rise to keep up with costs. His response, according to company lore, "If you raise the effing hot dog, I will kill you." Not metaphorically. Sinegal was known for his bluntness. He meant it. Since then, Costco has treated the hot dog price the way other companies treat their mission statement. Sacred. Untouchable. The board of directors knows not to touch it. New CEOs are briefed on it before they take office. It's written into the culture. You do not raise the hot dog price. Costco sells about 100 million hot dog combo units a year. Adjusted for inflation and ingredient costs, they're losing something like 30 to 50 cents on every single one. That's somewhere between $3 and $5 million a year in losses, just to keep a price stable. Why would you do that? Because of the question it answers. Every time a member sees that $1.50 price, they're unconsciously asking, "Does Costco respect me as a customer?" And the answer is right there on the food court sign, yes. So much that we lose money to prove it. It's the opposite of price gouging. It's price honoring. And it's why people are willing to pay a membership fee to shop there.
If I told you that you could reduce your pain just by believing you've taken a painkiller, even if the pill was fake, you'd probably be skeptical. You'd say, "That's just distraction. It's in my head." And you'd be right, in a way. It is in your head. But what's happening in your head is a real, measurable neurochemical event. This is the placebo effect, and for decades, doctors treated it like a nuisance, a confound to control for in clinical trials. But in the last 15 years, neuroscience has revealed something stunning. Your brain has the ability to manufacture its own painkillers, and expectations are the trigger that activates this system. Here's what happens. When you expect a treatment to work, when a doctor tells you this injection will relieve your pain, and you believe them, your prefrontal cortex, the thinking part of your brain, sends a signal down to the anterior cingulate cortex, a region involved in pain processing. That signal says, the pain threat has been evaluated, and we have a plan. We're going to handle this. And then, in response to that expectation, your brain releases endogenous opioids, neurochemicals chemically identical to morphine, but made inside your own body. These opioids bind to receptors in the insula, the nucleus accumbens, and the periaqueductal gray, all regions involved in processing pain signals. And suddenly, that pain signal gets quieter. Not because the injury is different, but because your brain has actively suppressed the message. The evidence for this is dramatic. In one study, researchers gave Parkinson's patients a placebo injection and told them it was dopamine. The patients showed motor improvement. Their tremors reduced, their stiffness eased. And when researchers used PET imaging to look at their brains, they found actual dopamine release in the striatum, the region involved in motor control. The belief had triggered the release of a real neurotransmitter. In another study, they gave people a placebo painkiller, and when they injected a drug that blocks opioid receptors, naloxone, the placebo stopped working. This proved that the placebo effect was operating through the opioid system, not through some generic positive thinking mechanism. What's especially striking is how fast this happens. Expectations can induce neural changes within minutes. Your brain doesn't gradually calm down. The moment expectation is established, the neurochemistry shifts. Now, this doesn't mean placebo works for everything. It doesn't cure infections or heal broken bones. But for conditions where the brain has direct control, pain, nausea, fatigue, motor symptoms, expectation can have real, measurable effects. Your brain, in other words, is a more sophisticated pharmacy than we ever gave it credit for. The lesson here challenges how we think about real versus psychological medicine. There's no such divide. Your mind is your brain, and your brain is biochemistry. When your expectation changes your neurochemistry, that's not a placebo effect that's somehow lesser than a drug. That's your biology responding to information, exactly as it's designed to do.
In November 1944, at Johns Hopkins Hospital in Baltimore, a surgeon named Alfred Blalock was about to attempt something that had never been successfully done before: open heart surgery to fix a congenital heart defect called tetralogy of Fallot, a condition that turned babies' skin blue because their blood wasn't getting enough oxygen. The patient was an 18-month-old girl named Eileen Saxon. The stakes were simple: the surgery worked or she died. What nobody in the waiting room knew, what very few people in the hospital actually knew, was that the surgeon about to perform this groundbreaking procedure wasn't doing it alone. Behind him, on a step stool, stood a man named Vivian Thomas, whispering instructions. Vivian Thomas was officially listed as a janitor at Johns Hopkins. He had no medical degree. He'd never attended college. At 19 years old, during the Great Depression, he'd started as a carpenter's apprentice when a surgeon named Alfred Blalock offered him a job as a lab assistant at Vanderbilt University, $3 a day, to help with animal experiments. He took it because he needed the work. But something happened in that lab. Thomas began reading medical textbooks, anatomy texts, anything he could get his hands on. He learned to dissect. He learned to think in 3 dimensions about the body's systems. And when Blalock began researching whether it was possible to surgically fix a baby's malformed heart, Thomas was the one who spent over a year alone in the laboratory, performing the same procedure over and over on dogs, refining the technique, proving it was possible. He didn't just follow instructions, he invented. When the standard surgical needles were too large for the delicate work, he took needles from the lab, chopped them down, and held them steady with a clothespin. He designed the specific way the surgeon would need to approach the heart. He worked out the angles, the timing, the sequence. Then came November 29, 1944. Blalock performed the surgery on Eileen Saxon, and she survived. She lived a full life after that operation. It was a miracle. And the newspapers, the medical journals, the Time magazine article that followed, they all credited Blalock and Helen Taussig, a physician who'd conceptualized the problem. Nobody mentioned Thomas. His name didn't appear in the Journal of the American Medical Association. He wasn't in the photographs. When Time magazine ran the story, it was the surgeon and the physician. The innovation was theirs. Here's where the story gets complicated, because it's not just about race, though that's certainly part of it. Thomas was denied credentials not because he lacked skill, but because he lacked the formal pieces of paper society required. No college degree meant he couldn't apply to medical school. No medical school meant he couldn't be legally called a surgeon, even though he performed the most delicate work in the operating room. The institution classified him as janitor, because that was a category that existed for a black man doing sophisticated work. It was easier than creating a new category, easier than acknowledging the truth. Thomas kept working. He and Blaylock developed more procedures, published papers that Blaylock signed but that Thomas had designed. And for decades, almost nobody outside the hospital knew his name. In 1971, Johns Hopkins hung his portrait in the hospital. In 1976, they gave him an honorary doctorate. In 1977, at age 67, he published his autobiography, Partners of the Heart, and the world finally started to learn the truth. By then, he'd been retired for years. By then, he was already being written into history by others, rather than being recognized in real time for what he'd actually done. The reason to tell this story isn't sentimentality. It's this. Vivian Thomas invented modern cardiac surgery, not despite being excluded from recognition, because of the specifics of how he was excluded. Institutions didn't deny his brilliance out of obvious malice. They just had systems that made his invisibility the path of least resistance. He got paid less. He couldn't advance formally. He couldn't attend the prestigious conferences. He couldn't see his name in print for his own work. But the work happened anyway, at 3 in the morning in a lab, or standing on a stool beside a surgeon, whispering what came next. And the miracle of modern heart surgery is inseparable from that invisibility. We remember the doctors. We barely remember the man who taught them how.
Stand on a street in Barcelona's Gothic quarter, and something invisible is happening in your brain. Your arousal is rising. Your attention is sharpening. You're not thinking about why. You're just feeling it. The street feels alive. But you could measure it. You could put a sensor on someone's skin and watch their conductance jump. You could put an EEG headset on their scalp and watch their prefrontal cortex light up. Something about this place is waking you up. And it's not the people, though they help. It's the streets themselves. Now imagine a different city, or a different part of the same city. Wide boulevards, blank walls, uniform building heights. Ground floor is a parking garage or a chain store, with nothing behind the glass but shadow. The ceiling is the sky, 100 meters up. Your brain responds differently. Skin conductance drops. You walk faster. Your mind quiets. Not because anything is wrong, but because the architecture is speaking a language of indifference. Researchers at the University of Waterloo ran a simple study. They had people walk past different storefronts in Manhattan while wearing skin conductance sensors. Basically, biometric bracelets that measure arousal the same way a lie detector does. When people walked past a blank wall or a Whole Foods with a minimalist facade, their arousal dropped. They quickened their pace. They wanted to leave. But when they passed a restaurant with varied windows, with an ornate building face, with detail and complexity, their arousal went up. They slowed down. They looked. Their brains were more engaged. This isn't subjective. It's not cultural. It's not about whether you like old buildings or new ones. It's a response built into how human vision and attention work. Your eye and brain are designed to find complexity interesting. A plain surface requires nothing from you. You can ignore it while walking. But a facade with window variations, with depth, with shadow and light creating texture, that demands attention. Your visual system has to work. And when your visual system works, you feel more alive. Add another element, green space. When people can see trees, parks, or green facades while moving through a street, their stress biomarkers drop. Vancouver, consistently ranked as one of the world's most livable cities, has zoning rules that keep mountains and forests visible from most neighborhoods. That's not incidental to why it feels good, it's the reason. That view is doing the work. And then there's the experience of navigation. The Seattle Central Library is architecturally striking, all clean lines and modern design. But its interior is notoriously confusing. One-way escalators. Unclear exits. When researchers tested it, people reported higher anxiety. Not because they disliked the building, but because their minds had to work harder to understand where they were and where they were going. Confusion creates low-level stress. Clarity creates ease. There's a formula here, and designers know it. Street width, building height. The ratio between them determines whether you feel enclosed or expansive. Window patterns, the amount of visual information in the facade. Whether you can see the sky or whether the buildings lean in over the street. The presence of trees, the possibility of stopping, sitting, eating. The existence of ground-level complexity, shops, cafes, doors that open to life rather than blank walls. When all these elements align, complex detail, good proportions, green visible somewhere, something interesting at street level, something to look at that isn't boring, you feel something. You don't think about it, you just feel present, you exist more fully in that moment. That's not poetry. That's architecture speaking the language your brain understands. Every city is telling you something. You just have to learn to listen.
You probably think you can multitask. Most people do. And the feeling is real. It feels like you're doing multiple things at once. But neuroscience has a spoiler. Your brain isn't built for it. Not for complex work, anyway. When you're doing something that requires genuine cognitive effort, writing, coding, design, analysis, your brain isn't splitting attention. It's switching. Rapidly, and every single switch costs you. A Harvard Business School researcher looked at knowledge workers, people like you, at desks working on computers, and found they toggle between applications and websites an average of 200 times per day. That's roughly once every 30 seconds. Each switch seems instant. You click a Slack message, you're back to it in a second. No big deal, right? Wrong. Cognitive scientists call what happens next attention residue. When you switch tasks, your attention doesn't immediately follow. Part of your mind stays on the task you just left. You're not fully present in the new one. You're fragmented. Here's the concrete number. After a single task switch, it takes an average of 25 minutes and 15 seconds to fully regain focus on the original task. Not to remember where you were, to actually get back into the cognitive zone where you can do your best work. That's the deep, focused state neuroscientists call flow. That's the state where real work happens. Let's do the math. If you're switching tasks every 30 seconds, and each switch costs you 25 minutes of focus recovery, but you don't actually recover because you switch again before 25 minutes pass, what you're essentially doing is working in a constant state of partial attention. Your brain is never fully in the game. This isn't a marginal productivity loss. This is hours. If you make 20 significant task switches in a workday, that's theoretically 500 minutes over 8 hours of focus recovery you won't get. You'll feel busy. You'll end the day exhausted, but you won't have actually done much deep work because you never had 25 uninterrupted minutes to do it. The design of modern work, notifications, Slack, email, calls, is essentially engineered to prevent this. You're not failing at focus. You're succeeding at distraction. By design. The human brain doesn't genuinely multitask when performing complex cognitive work. What it does is task switching, and each transition is measurable, costly, and cuts into your working memory. When you're deep in a coding problem or writing an essay, your prefrontal cortex, the part of your brain responsible for executive function, attention, and decision-making, is fully engaged. When you switch, that work gets interrupted. Your brain has to load a new context. It's like rebooting. The solution sounds simple, but it's almost shockingly rare in modern work. Uninterrupted blocks of time. Not 3 15-minute slots, not 90 minutes with a phone nearby. Genuine, protected time, where you're not context switching. Research on deep work shows that even 90 minutes of uninterrupted focus on a single complex task produces better outcomes than the whole day of fragmented work. Not slightly better, significantly better. The quality difference is noticeable even to you. The reframe isn't work harder, it's work in blocks. Identify your most cognitively demanding work, the work that actually requires your brain at full capacity, and build a 90-minute block where you're not switching. One window, one task, notifications off, no email, no Slack, just you and the problem. Does this feel impossible? That's the design working as intended. Your tools have trained you to interrupt yourself every 30 seconds, but the cost is real. Attention residue, cognitive fatigue, stress hormones elevated, and creativity suppressed. The paradox is that protecting time from switching isn't selfish or inefficient. It's where the actual work happens. Everyone around you will be fine without your instant response for 90 minutes. And you'll produce work that's measurably better for having had those uninterrupted minutes. Context switching isn't a productivity hack. It's quicksand. And the way out isn't discipline. It's design. Designing your time and your environment so the switch every 30 seconds trap doesn't claim you.
In the 1950s and 60s, a sleep researcher named Nathaniel Kleitman was studying sleep cycles in the lab. He noticed something odd. The 90-minute cycle he observed in sleep, moving from light sleep through deep sleep and into REM, wasn't unique to sleep. The body maintained a similar rhythm during the day, awake and moving through the world. Kleitman called it the Basic Rest Activity Cycle, or BRAC. Roughly every 90 minutes, whether you're asleep or awake, your brain and body go through a pattern. 90 minutes of peak alertness and focus, followed by a natural 15 to 20-minute trough where you slow down and your brain essentially asks for rest. Most people spend the trough fighting it. That's where the afternoon crash comes from. You wake up, your circadian rhythm is climbing, adenosine is dropping, and you're in the upswing of an ultradian cycle. For the next 80 to 120 minutes, your brain waves are faster, you're focused, ideas flow, you can push. This is your biological peak focus window. Then, without warning, something shifts. Around the 90-minute mark, your brain waves slow. Your attention gets fuzzy, you feel a little dreamy. You start scrolling instead of writing. You get up for a snack you don't need. You feel less sharp. This isn't a sign you're lazy or that your coffee wore off. It's a signal from your body that you've moved into the rest part of the cycle. And it only lasts 15 to 20 minutes. You don't have to fight it. If you rest, walk, breathe, do something easy, you'll naturally cycle back up. Most people hit 2 to 3 p.m. and feel a wall of fatigue. They blame it on lunch or sugar crash or not enough coffee. What's usually happening? They've already completed 2 full 90-minute cycles since waking at 7 a.m. They're in the trough of the third cycle. Their brain is legitimately in rest mode. Instead of honoring that, they fight it with more caffeine or push through. Fighting the cycle extends the low. Resting during the trough, even 10 to 15 minutes of walking, breathing, or a real break, lets the cycle complete. You bounce back sharper than if you'd battled through. Kleitman also observed something fascinating. In infants, the brain operates on a much shorter cycle, roughly 50 minutes. That's why babies nap constantly. As we grow, the rhythm extends. By adulthood, it settles into the 90-minute pattern. We didn't lose the need to rest. We just stretched the time frame, but the body still remembers and still needs the rhythm. Some people fight this their whole lives, thinking an afternoon dip means they're falling apart. Others learn to read the rhythm and work with it. It's the difference between resisting your biology and collaborating with it. Knowing about the 90-minute cycle changes how you build your day. Instead of fighting the trough, you schedule a real break in it. Not a fake break, scrolling your phone, but something your body recognizes as genuine rest. A walk, real food, a conversation, a few minutes of quiet. You're not lazy if the trough comes. You're rhythmic. The system is working as designed. You just have to listen to it instead of override it.
In January 2007, Netflix added a feature called Watch Now. Subscribers could stream movies instantly to their computers. Sounds normal now, right? In 2007, it barely worked. The internet couldn't handle the bandwidth. Videos buffered constantly. The selection was tiny. Wall Street investors looked at it and shrugged. Netflix's core business was DVDs by mail. This was a toy, a distraction, something to tinker with on the side while the real money came from red envelopes and mailboxes. Netflix executives, including founder Reed Hastings, saw it differently. They saw the future, and they were willing to lose money for years to get there first. Here's what Netflix knew that investors didn't. Streaming content wasn't valuable yet, because nobody was streaming. So licenses were cheap. Netflix made a deal with Starz in 2008. The studio gave Netflix access to 2 500 titles for a reasonable price, betting that streaming would never amount to anything. Netflix was essentially saying, let me buy all the Starz movies, while they're worthless. By 2012, Netflix was spending over $1 billion a year on content licensing. The price had gone up tenfold, but Netflix had already locked in cheap deals before the market realized what it was doing. That's not luck, that's strategy. Hastings bet that streaming would eventually work, that someone would solve the bandwidth problem, that internet speeds would increase, that people would accept watching video on screens instead of going to Blockbuster. He bet early. Here's the sacrifice part. Netflix's DVD business was massively profitable. It generated almost all of Netflix's revenue and all of Netflix's profit. When Netflix launched streaming, they offered it for free to DVD subscribers. No extra charge. Use both services, same monthly price. For 5 years, 2007 to 2012, Netflix's streaming service lost money. The content cost more than the revenue it generated. But the DVD business was so profitable that Netflix could absorb the losses and still be solvent. They were using the old business to fund the new one. Most companies can't do that. Most companies have to protect the legacy business. Netflix had the courage to cannibalize itself. By 2011, Netflix expanded to Canada. By 2012, they expected to return to global profitability. The sacrifice was almost over. Here's what makes this a real story. It worked. The internet got faster. Devices got better. Streaming stopped buffering. And Netflix's investment had already positioned them as the default streaming service. When everyone realized streaming was the future, they had to go through Netflix to get there. DVD rentals started dying. Netflix switched to streaming as primary, DVDs as the afterthought. Hastings had seen it coming 5 years earlier, and by the time the world caught up, Netflix already owned the space. Most companies can't afford to lose money on the future. Netflix could because they owned a profitable past, and they had the vision to know which way the wind was blowing. That combination is rare. That's why they won.
Imagine if every time you heard a piano note, a specific color appeared in your visual field. Not metaphorically, actually. A trumpet plays a high B, and you see crimson. A cello plays a low D, and the world shifts to deep purple. For about 1 in 25 people, this is just how reality works. They have synesthesia, a condition where stimulating one sense automatically triggers perception in another sense. For a long time, we thought this was neurological damage, a wiring mistake, but geneticists have recently discovered something that flips that assumption on its head. Synesthesia isn't a mistake. It's what remains when the brain fails to prune away connections that we're all born with. Here's the surprising part of human development. Your brain starts out hyperconnected. When you're born, you have neurons making connections across sensory regions, the auditory cortex wiring into the visual cortex, the gustatory regions linking to the olfactory. In most of us, these cross wires get pruned away during early childhood through a process called synaptic pruning. It's like your brain is saying, okay, sound and color are separate categories. Let me eliminate these redundant pathways. By adulthood, most people's brains are compartmentalized. Sound stays in the auditory system, color in the visual system. But in people with synesthesia, those connections don't fully prune. They remain. And when sound comes in, it automatically lights up the color processing region. When they see a letter, it triggers taste regions. The senses remain cross-wired. So what causes this incomplete pruning? That's where the genetics get interesting. Researchers sequenced the DNA of 3 families with synesthesia and found 37 genes of potential interest. But, and this is crucial, the genes differed across families. Family A had mutations in genes we'll call group X. Family B had completely different mutations. Family C had yet another set. What all these genes had in common was function. They regulate how neurons connect to the correct partners during brain development. Specifically, they're involved in axonogenesis, the process where growing neurons find and attach to their appropriate targets. And these genes are active in the auditory and visual cortex during the exact developmental window when synesthesia takes shape, around ages 5 to 7. So the biology seems to be, you inherit genetic variants that make it slightly harder for your developing brain to properly prune sensory connections. The result is that your brain keeps some cross-wiring that others lose. And from that intact architecture emerges synesthesia. What makes this fascinating is that no 2 synesthete families had the same genetic basis. This tells us that synesthesia doesn't arise from a single synesthesia gene that got copied wrong. It arises from multiple different routes to the same outcome, many different ways your brain's developmental machinery could preserve those cross-modal connections. And here's something else researchers discovered. The genetic mechanisms for synesthesia are similar to those implicated in autism spectrum conditions. Both involve subtle variations in how neurons wire up during development. Both involve enhanced connectivity in some regions. This suggests that what we're really looking at isn't synesthesia as an isolated oddity, but synesthesia as one expression of a broader principle. individual differences in sensory architecture. So when a synesthete tells you they see sound as color, they're not being poetic or exaggerating. Their brain is literally wired to experience the world that way. And their genome tells us that all of us started with that wiring. We just deleted it.